Assalamu alaikum. In this video, inshallah, we will solve about the actual Otto cycle. We already solved about the ideal Otto cycle, and in this video, we will continue with the actual Otto cycle. In this question, we have a spark ignition engine, also called SI engine, spark ignition engine, and also there is another name. It is the gasoline engine. Okay, when you see the spark engine, ignition engine, or the gasoline engine, SI engine, you will think about the Otto cycle, because Otto cycle, the spark ignition engines operate under the Otto cycle. Okay, يعني you will have a spark like this, and it will burn the air fuel mixture, but and this is called a gasoline engine. But in diesel engine, you will not have a spark. You will have instead of the spark, you will have a fuel injector. Okay. In SI engines, the combustion of the air fuel mixture is initiated by a spark plug. So the ignition itself is initiated by a spark plug. Otto cycle is the ideal cycles for the SI reciprocating engines. Okay. So when you see SI engines, think about Otto cycle. In diesel engine, it will be for CI engines, or and it will use the diesel cycle. Okay, it has a self-ignition temperature. But here we have a spark in the Otto cycle. Okay, has a compression ratio R equal to 8, an isentropic compression efficiency, and from this sentence we know that it is an actual actual Otto cycle. So isentropic efficiency and compression, so eta C, okay, or you can say it compression, okay, and it's equal to 85%, or when we use it in the equation, it is 0.85, and an isentropic expansion. So for expansion, some people put T because always, usually the turbine has an expansion process. So, but we don't have turbine here in the cycle, but so we can call it expansion only. Okay, it's 95% and equal to 0.95. At the beginning of the compression, if we saw the BV diagram, the compression process means the volume is decreasing from 1 to 2. So at the beginning of the compression process, isentropic compression process, so at state 1. So we are talking about state 1. At the beginning of the compression, the air in cylinder is at 13 pound square inch absolute. Okay, so P1 is equal to 13 pound square inch absolute. This is written like this: 13 pound force over squared inch, and it is relative to the absolute pressure. Absolute pressure. Okay, don't care about the units. We need in this video the idea of the isentropic efficiency and the actual cycle. Usually in the exams, the units is in SI units. Okay, not the British or the US customary units. Okay, and the temperature is 60 Fahrenheit. The tables, our thermodynamics tables in these units are in Rankine unit. It is a temperature unit, and you can add for this one 460 to be in Rankine. You can say that 1 Fahrenheit is equal to 460.67 Rankine. Okay. So I will add to this one 460. Let's ignore this 0.67 because like the Celsius and Kelvin, we ignore the 0.15 in the 273.15 in Kelvin. Okay, so 60 Fahrenheit plus 460 will give you 520 Rankine. Okay, so if you need to convert, it will be from, you can say the temperature in Rankine is equal to the temperature in Fahrenheit plus 460. Okay, the maximum gas temperature is found to be 2300 Fahrenheit. So the maximum temperature, where is the maximum temperature in TS diagram? The maximum temperature, you can see here, is state 3, the highest temperature. Okay, so this value 2300 Fahrenheit is for T3. So T3 is equal to 300 Fahrenheit, and in Rankine I will add 460, so it will be 2760 in Rankine. Okay, because the thermodynamics tables are in Rankine. Determine the heat supplied. Heat supplied, it is Qn here from T2 to 3, so Qn per unit mass, that is why it is small q. Okay, the thermal efficiency and the mean effective pressure. Okay, so I will solve using two methods, the constant specific heat and variable specific heat. In the question he said constant specific heat, we will use this one first, then we will go to the variable specific heat, and we will see how to use the isentropic efficiency with each one of them. Okay, let's start with Qn. Qn for constant specific heat, cold air standard assumption, we use this equation. Qn is equal to Cv times T3 minus T2. Okay, I have T3 and Cv. I can get Cv from the table, yeah, the thermodynamics table. Thermodynamics table for this unit is here, table A1E, I think. Yes, our table A2E. Okay, A2E in this unit is 0.171. So this one is Cv. If you want to find R is 0.06855 for air. K is 1.4. So you can get the values from here. Okay, where we are. We need to find T2. So the problem is in T2. How can I find T2? I have the compression ratio R, okay, and R is equal to V1 over V2, so I can use this equation instead of V1 over V2 over V2, and I already have a T1, and I want to find T2. This T2 that I will find, it is T2S, the ideal one, okay, the ideal one, because this is isentropic relations, under isentropic compression or isentropic expansion process. So this is for the ideal cycle. So this one is T2S. So what is the difference between ideal and actual Otto cycle? What is the difference in, for example, in the TS diagram? Here, that is an isentropic compression process from 1 to 2. In actual Otto cycle, it will not be isentropic compression. It will be like this, and it will go from 1 and go like this to 2. This one will it will be called 2A, the actual state 2. Okay, and this one will be 2S. That is why I call this T2S, isentropic. S is constant, entropy is constant. Okay, and in the expansion process, it will not go from 3 to 4 like this. It will expand like this. No, is isentropic expansion. So this one also will be state. You can say it is state 4A, and this we will call it 4S. Okay, 4 for A for actual and S for isentropic or ideal cycle. Okay, ideal state. So for 1 and 3. There is no change. It is at the beginning of the compression and at the beginning of the expansion. It is the same for actual and ideal. So the problem is between 2 and 4. Okay, 2 actual, 2 ideal, and 4 actual, 4 ideal. The equation that relates between the actual and ideal cycle is the isentropic efficiency. Here is the equation. For Otto and diesel cycle, even dual cycle, at the compression process, they have this equation, T2S minus T1 over T2A minus T1. T1 is common between them. That is why it is in green. But there is an ideal temperature in red, and there is actual temperature in blue. Okay, and also for diesel and Otto cycle in expansion process, we have T3 minus T4A over T3 minus T4S. T3 is a common. It will not change, even it is actual or ideal cycle. But for state 4, we have ideal temperature and actual temperature. Okay, when you have a question with isentropic efficiency in the statement of the question or in the requirement of the question, so it is an actual cycle question. Okay, and you have to use the isentropic efficiency. Okay, and you cannot find Qn, Wnet, Qout, anything that he wants from you to find, even the mean effective pressure, unless you use the isentropic efficiency equations and find the actual temperature T2A and T4A. يعني you cannot solve using T4S or T2S. You have to use T2A and T4A because it is an actual cycle now. Okay, so our problem now is to find T2A and T4A. So when he asked about the Qn, the input or the heat addition in the cycle, T3 is the same, but T2 is for the actual. So I want to find T2A. And here this relation is only for the isentropic process. So it will give me T2S, and I cannot use this equation and find T2, then I substitute this T2 here in the equation and find Qn. No, I have, after I find T2S from this equation, the isentropic equation, I have to go to the isentropic efficiency relation here, okay, and use this equation. I have T1, I have the efficiency. I will calculate T2S from the isentropic relation, then I can go get the T2A, the actual temperature as state 2. Okay, that is the process. You have to solve first for the ideal. First solve for the ideal, then use the isentropic efficiency, then go to find the actual temperature. Okay, that is the way we will use, inshallah. So let's see, or let's solve using the isentropic relation to find T2S. Okay, T2S, I have T1 equal to R power K minus 1, because I already have R, and R is V1 over V2 or V3 over V4. Okay, so equal to R K minus 1, and T2S is then equal to T1 R K power K minus 1 is equal to 520 in Rankine times 8 power 1.4 minus 1. So T2S is equal to 1195 Rankine. Okay, now I get T2S. Do not substitute T2S in Qn. Qn you find the actual heat addition, because it is actual question, actual ideal, actual Otto cycle. Okay, so let's find the actual temperature. And to find the actual temperature, we already find the ideal temperature. Okay, we'll use the isentropic efficiency from here. It is a compression, isentropic efficiency compression, because we are talking about state 2 in the compression process. Okay, in the compression process from 1 to 2. Okay, so we are comparing the compression process between the temperature at the beginning of the process and the ending temperature. The temperature at the beginning is the same for the actual and the ideal. Okay, so let's use this equation. It will be the isentropic efficiency for the compression of Otto cycle is equal to T2S minus T1 over T2A minus T1, and this will give you that T2A is equal to T1 plus T2S minus T1 over the isentropic efficiency of the compression. So T2A is equal to T1 is 520 Rankine plus 1195 minus 520 Rankine over the isentropic efficiency 0.85. Don't write it 85%, put it 0.85. Yani if he gave me you in the question 85%, means 85 over 100, and 85 over 100 from the calculator, it will give you 0.85. Okay, so this one will give you 1314 Rankine. Okay, that is for T2A. Now I have T2A, and I already have T3, and T3 is same for the actual and ideal. So I can CV from the table, I can get Qn. So let's find Qn. Qn is equal to CV T3 minus T2A, the actual one. Okay, Qn is equal to CV from the table is 0.171. T3 is 2760 minus 1314 will give you 247.3 BTU over pound mass. BTU is like kilojoule يعني, and pound mass is like kilogram. Okay, don't care about the units يعني, we are focusing on the idea of the isentropic efficiency and the actual cycle. Okay, what is the next requirement? The thermal efficiency. Thermal efficiency is W net over Qn. Okay, W net over Qn. I already calculated Qn, but I don't have W net. W net is equal to Qn minus Q out. Okay, I have Qn, but I don't have Q out. So for Q out, it is CV T4 minus T1. T1 I already have it from the question, but T4 I don't know T4, but I will do the same procedure that I did with T2. This one is T4A. I have to calculate T4S first from the isentropic relation. This one is T4S. Then I can go to the isentropic equation, isentropic efficiency equation. Then I can find the T4 actual. Okay, so let's find T4S first. So T4S, or you can say T3 over T4S is equal also R power K minus 1. So T4S is equal to T3 over R K minus 1, and it's equal to 2760 over 8, 1.4 minus 1, and this will give you 1201 Rankine. I found T4S. Let's use the isentropic efficiency equation for the expansion. This one, okay. Between the states 3 and 4, they are the states for the expansion process. Okay, the expansion process from 3 to 4. Okay, isentropic expansion. If it is ideal, now it is not isentropic expansion. Okay, you can see here it is not isentropic. The S is not constant. S3 is not equal S4 now. Okay, so let's write this equation for expansion. T3 minus T4A over T3 minus T4S. If you want to find T4A, it will be equal to T3 minus the efficiency of the expansion, okay, times T3 minus T4S. So T4A is equal to T3 from, it is given in the question, 2760 minus for the expansion isentropic efficiency, it is 0.95. This one is 2760 minus 1201, and this will give you T4A is equal to 1279 Rankine. Okay, now I can find Q out. Q out is equal to CV T4A, the actual one, minus T1. CV is 0.171. Okay, T4A is 1279 minus T1 520. Q out is equal to 129.8 BTU for pound mass. Then finally I can find W net, and from W net I can find the isentropic, the thermal efficiency. Okay, Qn minus Q out will give you 247.3 minus 129.8, and W net will equal to 117.5 BTU per pound mass. Okay, the thermal efficiency is equal to W net over Qn. W net is 117.5, Qn is 247.3, and this will give you 4.75 0.475 and equal to 47.5%. Okay, for the last part, the mean effective pressure. From the last video, we knew that the most used equation is W net over V1 1 minus 1 over R. Okay, W net is 117.5, and for V1 you have to calculate it using the ideal gas law, V1 equal to RT over V1. Okay, RT1 over V1. R from the table, R is from the table for air in this unit. We have the temperature and pressure are in Rankine, and the pressure in pound square inch. That is why I will use this one, 0.3704, because the pressure in the question is given in pound square, pound per square inch, or pound squared PSI, pound per square inch, pound squared inch, pound squared inch, pound squared inch, pound squared inch, pound per squared inch. Yani don't care about the units, okay? But for this unit, that is why we will use the R using PSI, pound squared inch, absolute, but we don't have the BTU over pound mass. Okay, that is why the R is like this 0.3704. This pound over inch squared, or pound times inch squared? I don't know. Okay, 13 will give you 14.82 feet cubed over pound mass. So the mean effective pressure will be equal to 14.2821 minus 1 over R is 8, and this will give you 9.06 BTU over feet cubed. But يعني we usually use the pound squared inch, and I don't know when we are using it يعني so we have to multiply by a factor that is 1 BTU. I actually didn't find any question about actual cycle in SI units, so that is why I am solving with these units. And even I looked for a question in other books, I didn't find. Okay, so that's the only question that we have. And I will multiply here by 5.404, and it will give me 49 pound squared inch absolute. Okay, so the answer will be 49. Yani you don't care about the numbers or the units, because usually we will have SI units. Okay, that is the way of solving using the isentropic efficiency or the actual cycle. We solved using the constant specific heat. So I will read the question again, by using the variable specific heat. Okay. So let's solve the question using the variable specific heat. Let's write our givens again. We have the R is equal to 8. Let's use different equation, like the blue one. The isentropic efficiency of the compression is 85% and is equal to 0.85. The isentropic efficiency of the expansion is equal to 95% or equal to 0.95. B1 is this 13 pound squared inch absolute. Okay. T1 is 60 Fahrenheit plus 460 Rankine, and it will give you 520 Rankine. Also we have the T3 is equal to 2300 Fahrenheit, and it is equal to 276 Rankine. and we need to find the Qn thermal efficiency and mean effective pressure, but using variable specific heat. Okay, so and we will say it is actual Otto cycle. Okay, and we will use the variable specific heat. Okay, let's see. For variable specific heat, we want to find Qn. Qn is equal to U3 minus U2. For U3, if I have anything like VR3, T3, and T3 is S يعني, or يعني, it doesn't matter it is S or actual, and T3 is common between the actual and ideal one. The problem is in U2. U2, I have to find U2 at an actual temperature T2A. Okay, I cannot find it at T2S. So let's draw again the difference between the actual and ideal. This one is T2A, and we'll call this one T2S, and this one will be an expansion. This point will be for A, and this is for S. So T2A, how can I find T2A? I don't have, I know I have the isentropic relation, but the problem, how can I find T2S? T2S, I don't have any other option than using table A17. And after using table A17, I can use the isentropic relation, okay, and find T2A. And after I find T2A, I will go again to table A17 with T2A. So I will use table A17 two times at state 2 to find T2S. Then I can find, using the isentropic relation for compression, T2A. Then from T2A I can find U2 using table A17, and here also I will find T2S from table A17. Okay, but I don't have anything at state 2, so I can use and find T2S. يعني in table A17, I need only one property, so I can find any other properties, right? Okay, so let's go down. This weird tables. Okay, for air. So if I need to find a temperature, I have to have H, VR, U, VR, any one of them. Okay, usually in this cycle we knew that we use VR, okay, the relative volume. Okay, for the relative volume, so I need the relative volume because I want to find U2, so I cannot use U to find T2, and already I want to find U2. So the only option is to use VR. So I need VR2, and to find VR2, I have the compression ratio. That is the only equation that contain VR2. I have the compression ratio R. Okay, I have R, but I don't have VR1. So I need also to find VR1. And how can I find VR1? Do I have any state at state 1? Yes, it is given in the question that the temperature at state 1 is equal to 276. This one is T3. T1 is equal 520 Rankine. Okay, so using T1, I go to the table A17, and find VR1, and from VR1 I will use the compression ratio. Okay, so I can find VR2. From VR2 I will find T2S using table A17, and from table A7, after I find T2S, I will go to use the equation for the isentropic efficiency and find T2A, and from T2A I will go to table A17 and find U2, and then after finding U2 I can find Qn. Okay, and there will be a lot of interpolation. So if you already know how to solve this question and you already got the idea, just leave and don't waste your time, go for any other video. Okay, so let's go. First, I have I want to find what? I want to find we said I want to find VR1, so I will go using T1 equal to 520 ranking, and to find VR1. Okay, so let's go to table A17, 520. Okay, and this one is VR1, and so VR1 is equal to 158.58, and it's dimensionless quantity. Okay, then I will use R equal to VR1 over VR2. So VR2 is equal to VR1 over R. VR1 is 158.58 over 8. So so VR2 is equal to 19.823. I will use this VR2 to find T2, but it is T2A, T2S, okay? T2S. First we will find the ideal, then we can use the isentropic efficiency, so we can go finally find the actual temperature. Okay, so VR2 is 19.823, so I will go and search for 19.823. It is between these two numbers, okay? Between these two numbers, so I will make an interpolation. Always you will make interpolation. So it will be like this: T and VR 1160. I want to find T2S, and here is 1200, 20.29. My VR2 is 19.823, and this will be 18.51. So T2S minus 1160 over 1200 minus 1160 equal to 19.823 minus 20.29 over 18.51 minus 20.29. So T2S is equal to 1170.49 Rankine. I got T2S, so now I can find using the isentropic compression efficiency, I can find T2A. So the isentropic compression efficiency is equal to 2S minus T1 over T2A minus T1. If I want to find T2A, it will be equal to T2S minus T1 over the isentropic efficiency plus T1, and this will give you 117.049 minus 520 Rankine over 0.85 plus 520, and this will equal 1285.3 Rankine. Okay, now I found T2A. I will use this value and go to the table, okay, to find the U2. Okay, from here I want to find U2. Okay, let's use this number 1285.3. 128 is here between these two numbers. Okay, so this column for U, so I will use 224.05, 231.63 with 1280 and 1320, and here is my temperature is between these two numbers. It is T2A, and is equal to 1285.3. so let's make interpolation. So between T and U, 1280, my T2A is equal to 1285.3, and this one is 1320, 224.05. U2, I want to find U2, 231.63. So 1285.3 minus 1280 over 1320 minus 1280 is equal to U2 minus 224.05, 231.63 minus 224.05. Okay, U2 is equal to 225.05 PTU over pound mass. Okay, Qn we know it is equal to U3 minus U2. I found U2, but I didn't find U3. U3 I can get it from T3. Okay, T3, yeah, it doesn't matter S or A. Actually, it is the same for both. Okay, so T3 is already equal to what? T3 is equal to 2760 Rankine. So I will go to the table also. 2760 Rankine is here. Okay, between these two numbers, and I will do interpolation so I can find U3. U3. Okay, let's make also another interpolation. So T U 2750 2760 2800 529.31 U3 540.40. So 2760 minus 2750 over 2800 minus 2750 is equal to U3 minus 529.31 540.40 minus 529.31, and this will give you U3 is equal to 531.528 BTU over pound mass. So finally Qn will equal to U3 minus U2 equal 531.528 minus 225.05. So Qn is 306.478 BTU over pound mass. And then the thermal efficiency, the second requirement, is equal to W net over Qn. W net is already Qn minus Q out, but I don't have Q out. I got Qn, but I don't have Q out. The equation for Q out is U4 minus U1. Q out is U4 minus U1. I didn't found U1, okay, but I can use the table to find U1, right? I didn't find U1, okay, and also for U4 I need to find U4. It is the same problem like for U2, so we'll follow the same procedure that we draw here, okay. For U4 I need to use find U4 so I can find Q out, okay, and to find U4 I need to find T4A, and T4A is from the equation for the isentropic turbine or isentropic expansion efficiency, okay. And this one, to use this equation, I have to find the T4S, and before T4S, I have to have any property at state 4. I cannot use U4 because I already want it here. So the only solution is to use VR4, and for VR4, okay, I don't have VR3. That is the only equation that contains VR4. So I need to find VR3 first, and to find VR3 first, okay. Also, I will use it with R. To find VR3, I have to have a number or a property at state 3. I have T3, okay. So I will use T3 to find VR3. Then I can find VR4 using R, and from VR4 I will use also table A17 to find T4S, and from T4S I will go to the isentropic efficiency expansion, and then I can find T4A, and we will go again to table A17 using T4A and find U4, and finally I can get Q out, okay. So the same procedure again, but for state 4, okay. So let's make interpolation using for T3, so T3 is equal to 2760 Rankin. And I told you already that at each state you have to find everything. And already we made an interpolation, somewhere here for T3. T3 is here, and we found U2. So if we already found VR again, so VR with U at the beginning, it will be easier for us. So at each state, just find everything. So if we wrote here VR, okay, VR, and if you go to the table, you will find that it will be 1.566, and here is VR3, and this one is 1.478. Okay. So I will also write here VR3 minus 1.566 over 1.478 minus 1.566. So VR3 is equal to 1.5484. I will use VR3 with the compression ratio, so I can find VR4. So I will say that R is equal to VR4 over VR3. Then VR4 is equal to R VR3. R is 8 and VR3 is 1.5484. So VR4 is 12.39. Okay. Then from VR4, I will make interpolation to find the temperature. So let's see the 12.39. 12.39 is here. I will make interpolation between these two numbers to find T4S. Okay, it will be between 1360 and 1400 using 13.12 and 12.1 because my VR is 12.39. So let's make another interpolation. Okay, TVR. I want to find T4S and 1400, 13.12, 12.39, 12.1. Okay, so this will be equal to T4S minus 1360 over 1400 minus 1360, and is equal to 12.39 minus 13.12 over 12.1 minus 13.12. So T4S is then equal to 1388.63 Rankin. And from T4S, I will go and use the isentropic efficiency expansion. Okay, the isentropic efficiency expansion, and it is equal to T3 minus T4A over T3 minus T4S, and I want to find T4A. T4A is equal to T3 minus the isentropic expansion times T3 minus T4S. Okay, for T3 is 2760 minus 0.95. That is the isentropic efficiency for the expansion, 0.95. T3 is 2760 minus T4S is 1388.63, and it will give you T4A is equal to 1457.2 Rankin. Okay, now finally I found T4A. I will use T4A to find U4. Okay, so I will go to the table 1457.2. 1457.2 is here between these two numbers, 1440 and 1480. So I can find a number U between these two numbers. Okay, for U4. So I'll make again interpolation. So I don't see that this question will come in the exam, and if it will come in the exam, it will be in constant specific heat. It will not be in the variable specific heat. Impossible. Yeah. Okay. 1440 T4A is equal to 1457.2 1480 U is 254.66 and I need to find U4, 262.44, and let's make the interpolation. 7.2 minus 1440 over 1480 minus 1440, and this equal to U4 minus 254.66 over 262.44 minus 254.66. So U4 is equal to 258 BTU over pound mass. And finally, Q out is equal to U4 minus U1. And for U1 we didn't find it, okay, but we already used T1 to find something. I think VR1, okay. So also when we use if you want to find any property, find other properties along with the one that you are finding. Okay, so for VR1 also you can get U1 is equal to, so from T1 equal to 520, so U1 is 88.62, so it's equal to 88.62 BTU over pound mass. Okay, then Q out. U4 is 258 minus U1 88.62, and this will give you Q out is equal to 169.38 BTU over pound mass. For W net, it's equal to Qn minus Q out, and it's equal to 306.478 minus 169.38. So W net will equal to 137.1 BTU over pound mass. Okay, for the thermal efficiency, W net over Qn will equal 137.1 over 306.478, and the thermal efficiency will be 0.447 or equal to 44.7%. And for the mean effective pressure is equal to W net V1 1 minus 1 over R. V1 is from the, as you said, or as we saw before in the constant specific heat, the same equation, the ideal gas equation, R equal R times T1 over P1. R is 0.3704 for this units, okay. 520 the T1, B1 is 13 pounds squared inch absolute, okay, is equal to 14.82 feet cubed over pound mass. So let's substitute here 137.1 over 14.82, 1 minus 1 over 8, and we said that we want to convert from this unit BTU per feet cube to pound squared inch, so you have to multiply by 5.404. okay, don't care about this, inshallah in the exam it will be in SI units. Okay, and this will give you 57.134 pounds squared inch absolute. Okay, and as you can see, the thermal efficiency from the variable specific heat is less than the one for the constant specific heat, and this one is 44.7, and for this one is 47.5. okay, it is less. This one is 44.7% for the variable specific heat. Okay, the variable is more accurate, and the constant specific heat has an error in positive. Okay, that is for this question about the isentropic efficiency or the actual cycles. And thus for this chapter we have also the diesel and Dole cycle. diesel and dual cycle يعني you will have يعني approximately the same procedure. Okay, يعني nearly the same procedure. And the second part of the chapter is about Brighton cycle. It is an open cycle, but here these cycles, Otto, diesel, and dual cycle, we treat them like they are closed system. Okay, and only يعني a closed system because we ignore the intake and exhaust valves. We will talk about this intake and exhaust valves, exhaust valve process in the next video, inshallah. We'll talk about the 4-stroke engines and 2-stroke engines and how to solve a question about Otto cycle on these 2-stroke engines and 4-stroke engines, inshallah. Okay.